Hi, my name is Robert Veranek. I'm from FEDEVEL Academy, and in this video we are going to speak about perfect footprint. And of course, not this kind of footprint, but this one. After you finish watching this video, you should have a lot of information about how to create really good footprints. In this video we are going to speak about the size of the path, what you may want to consider when you are creating paths for any kind of footprint, what you may want to consider when you are creating mask or paste layer for your footprints, what to think about when you are designing the seal screen layer, when you are marking pin 1 location, or we are going to speak also about standards. You know, when you are creating footprints, there are some standards what you may want to follow. Should you follow these standards? What are these standards about? What is inside of these standards? What they tell you? And I would like to tell you, when I was creating this video, I learned a lot. Okay, so I really hope that this video will be interesting for you, and I really hope when you finish watching this video you will start thinking like, maybe in future when I'm creating new footprints I should not do it the way as I used to do it last 10 years. Maybe I should do it differently because of this video. That's what happened to me, okay? Once I started working on this video, I went back to my library and I was like, maybe I should change all these footprints because as I have it, that's not the best way I should use in my new board. So I really hope this is something what will be the result of watching this video. Now, I would like to tell you I'm not the expert for footprints, and the reason why I learned a lot when I was preparing this video is because I was very lucky and I could talk to Tom. Tom is the guy who is creating the standards about how to create footprints. He is the right person to ask if you would like to know anything about the footprints. And I was very lucky because Tom agreed to have a call. We actually had 2 calls. I recorded like I think more than 4 hours of audio and video, and I cut it down, these 4 hours. I pick up all the most interesting topics from these calls, and that's what I placed inside of this video. So enjoy the video, and I really hope you will find it useful. Here is the call. This is the key where we would like to go with this call. Here you can see a table which is very important because based on this table you can create a lot of footprints. But to actually understand what is inside of this table, we cannot simply just start speaking about how to create a perfect path for a component. First, we need to understand what is behind of creating the perfect path. So we are going to start with some little bit more simple topics, and so we understand what is behind of these numbers, what is behind of some of the terms which are here, some of the words what are used here, and then you will understand, when you have a look on this table, you will understand how to create a great path for all the kind of different footprints. We are going to start with something simple, which is explanation what is a good path about.
But it's these chips that they're of all kinds of varying heights, and all you got to do, I don't care how high the chip is, the J standard 001 says in class 3, all you got to have is a 0.5 millimeter, maximum, or G plus 25%, whichever is less. Okay, so what I wanted to get the slide in here because it's the J standard that's depicting that solder joint fillet. And so if I have to have a 0.5 millimeter fillet, that means that my toe out there, the toe is the part that's sticking to the right, out to the outside of the part. That means that my maximum toe could possibly be a 0.5 millimeter.
What? Maybe we should speak a little bit what we can see here, and also about a few things which are mentioned in this very short clip, so everyone understands what we are speaking about. So first, on this picture, you can see definition from this standard, which is here, JSTD001 standard. It specifies how this good soldering looks. Okay, and here in these few sentences, you can see all the kind of specifications for these dimensions, which will tell you if your soldering is good or not. Now, before we go further, I will play a little bit about this. I will play a little bit from our call about this JSTD001 standard, so you know what is this standard about. I will play a clip about these classes 1, 2, and 3, so everyone understand what these classes are about. And then also we will have a look on the other terms, like what Tom mentioned. He mentioned a toe. We will have a look what this toe and heel means. So first, have a look on this JSTD001 standard.
And then come along the IPC J standard 001, which is the solder joint goal acceptability. And then J standard 001, they have a lot of rules in there, but it's really interesting that the rules. And then in 7351, it says on the very first line in the document, very first word, it says this guideline it follows the J standard 001. Okay. And so the J standard 001 is the leading document. It's the leading IPC document, and it's for and people get tested to be CIDs or CITs. A CID is a certified solder person. They solder boards, whatever. It's for assembly process. And the CIT is a trainer. You become a certified interconnect trainer, where you train people how to become CIDs or whatever. And I'm a CIT. So when you study these documents, these IPC documents, okay, they don't really have anything in there about like a preferred pad shape, for instance, or outlines. We all know that there's a lot of outlines in a library part. There could be a silkscreen legend outline. There could be an assembly outline. There could be a component body outline. There could be a courtyard outline. Okay, well, there's really no guidance for the thickness of these lines, or for if you want to use a rectangular pad or a rounded rectangular pad or an oblong pad or whatever. And so what we did at PCB Libraries was.
And now you know what is this JSTD001 standard about. For us, it is important that this standard specifies how the good soldering should look. Now let's have a look on these class 1, 2, and 3, what these classes are about.
Class 1, it's for general products, okay? And this is for both assembly and for manufacturing. So class 1 is like I don't care if it fails or not. Could you imagine creating a printed circuit board and manufacturing it, and you don't care if it fails? Okay, So in this particular category, class 1 would be toys, okay? So there's lots of electronics in toys nowadays, and gosh darn it, if I go to the store and buy it and I bring it home and it works for a month or two and then it breaks, so what? I throw it away, or I give it to somebody else or whatever, you know. And see, for class 1, you know, it's like I want to make it cheap. See, class 1 is like really, really inexpensive to build. Okay, and so if I say I want to build my boards in class 1, that gives the manufacturers full reign to do sloppy. They could use slup, right? They could. I don't care about the registration. I don't really care about the silkscreen registration or the silkscreen if you can legible or not, or the solder mask or this or that or whatever. Okay, I could go ahead and freely build this board really cheap, and I could build it mass quantities to build massive amounts of millions of toys. Okay, and if they fail, they fail, and if they don't, they don't. But that's class 1. And then class 2 is a little bit more specific. It's for dedicated service products like computers. If I'm spending a lot of money on a computer, I surely don't want it to fail. And so like my cell phone, I don't want our webcast right now to be interrupted by my phone failure, right? And so dedicated products means that I bought it and I depend on this to work, okay? And it's, you know, it's typically the environment is kind of calm. I mean, I'm not using my phone. I could use it in a harsh environment. Here I'm in Arizona. I'm in Phoenix, Arizona right now. It gets to be 118 degrees here in the summertime or whatever, and the phone could be sitting in the car in 140-degree temperature in the car. So it has to withstand those temperatures. Or I could use the same phone in North Dakota, here in the United States. It's severe cold. It's 30 degrees below 0 Fahrenheit.
Yeah.
Okay? So the phone has to be reliable. Yeah, it has to pass these. It has to pass some tests: drop tests, stress tests, vibration tests. Yes. Thermal cycling. Yes. But class 3 is the mother of all high performance electronics. Okay. Class 3. If I put a class 3 on my fabrication notes, okay, that means that the manufacturer has to walk the boards through the whole process, through every single process in the manufacturing line, because class 3 means it can't fail. And if it fails, we're going to sue you. Okay? So basically, class 3 is medical equipment. You know what I mean? If somebody's on a dialysis machine or some kind of life support system, breathing or whatever, I mean, it absolutely is critical and it cannot fail. And that's a class 3 high performance printed circuit board. Okay. Also military and maybe weapons. You know, you don't want to have a weapon that fails in the battlefield. Okay. So I'd probably predict that 99% of all military printed circuit boards are class 3. Okay. And these are very expensive. See, where class 1 is very cheap, but class 3 is very, very expensive to build these class 3 boards.
Now we know about the classes, and we still would like to understand a little bit about toes and heels. So here is another clip from our call.
Explain on that 7351 about the difference between the toe and the heel. And I want to kind of like put it towards this foot, the human foot, okay? So we have the toe and the heel, okay? And I just want to give this as an example, because I'm going to change the slide again now, okay? Where we have these packages where in the beginning, I would say that maybe 10 years ago, IPC said that all the toes are on the outside and all the heels are on the inside. And then when somebody on the committee said, well, wait a minute, are you talking about the toe and the heel of a human foot? And they're saying, well, yeah, sort of, because we have a knee, you know, at where the lead comes out of the package is the knee, then you have the heel and then the toe. So IPC then changed some of the toes to be on the inside of the part.
This was interesting for me, because when I saw this picture, I was like, oh, sometimes the toe is inside under the component. I didn't know that. Yes,
because it forms the human foot. What's the human foot? The leg, the human leg and the heel and the toe.
And this is important because when you are creating footprint, and if you mix the heel with toe, then you get wrong footprint.
That's right. That's correct. Okay, so let's change the slide again.
This is a very important picture, and it's very important everyone understand what does it mean toe and heel. So the space or the part of the path which is between end of the leg and end of the path, in this situation this is what is called toe, and here what is behind the leg, this is what is called heel. Okay, and because the human leg explanation or comparison, in some components actually on this outside of the components there can be the heel and the toe can be under the component. And it's very important to recognize this and remember what the toe and heel is about, because these are the two things which are used to calculate size of your path. Now, when we go back to this picture, we should understand what we can see here. So this standard specifies the minimum height of this solder for chip components, for resistors and capacitors, and for class 1 and class 2 components, or this kind of components, resistors and capacitors, are well soldered when wetting is evident on the vertical surface of the component terminal. But if you are creating boards, or you are building boards for class 3, so like medical equipment, then the quality of the soldering, it requires this fillet to be at least 0.5 millimeter tall, or if the component is smaller, then it has to be at least 25% of the edge. And then you need to add also this distance which is between the PCB and the bottom of the component. Okay, so this standard basically specifies how this good soldering should look, and based on this a new standard was created which speaks a little bit closer about the kind of, or it's a little bit more specific about how to design footprints for specific components. So this one is about soldering, but we also have a standard or document which speaks how to create proper footprints based on this standard. So what standard we are actually interested about? Let's have a look.
Well, there are, but it gets down to granularization, okay? Because what happens is that the 610 is for fabrication, and then underneath that fabrication are all kinds of other standards. But 610 is the mother of all standards, okay? I mean, as far as fabrication goes, okay? Then we get into the J standard 001, which is for assembly, okay? And this is the mother of all assembly standards, okay? And everything else falls below this standard. So basically, the IPC 7351, which is the footprint land pattern standard, okay, it says generic requirements for surface mount design and land patterns. It's a standard, and it says the word standard here twice. It has standard there and standard there. This is a screenshot of the picture of the standard, okay? And it's no longer a standard. Since Dieter Bergman passed away 5.5 years ago, Karen McConnell, the chairman of the committee, took the word standard off and replaced it with the word guideline.
Mm-hmm. Okay, if you Google for all these standards, this is what you can find. 610, acceptability of electronic assemblies. 610 amounts to high-level inspection and passage requirements for printed circuit board PCB assemblies. Okay, then if we already had a look at this JSTD standard. It is about requirements for soldering, electrical and electronic assemblies. And then we have this IPC 7351, which is about surface mount design and land pattern standards. And as you can see, or as Tom already mentioned, it's not standard anymore. These documents are guidelines, so they will help you, or they will recommend you how these footprints maybe should be designed. Let's have a look what is inside of this 7351. What is this speaking about and how it is recommending you to design the footprints.
I'll show you this out of the IPC 7351. This is a copy and paste out of their standard for chips, okay? And for chips, they're saying basically they call them rectangular square end components or capacitors and resistors, whatever, right? And they're saying that the nominal density level for the toe should be 0.35 millimeters. Mm-hmm. But the J standard says, well, wait a minute now. If you have a height of a 4 millimeter height, I want a 0.5 millimeter fillet. Mm-hmm. How can you get a 0.5 millimeter fillet with a 0.35 millimeter toe? Mm-hmm. You know what I mean? So the standards kind of conflict with each other a little bit.
Let's stop for a moment, and we are going to have a closer look at these two tables which are here. So these tables are from the IPC 7351 standard, which is recommending the land pattern or footprint. And these tables are telling us the recommended values for the toe. Now we know what does it mean. Toe is the distance between end of the path and end of the component leg. Okay, so these tables are speaking about the toe size, recommended toe size for the chip components. Chip components are, for example, these SMD capacitors and resistors, and we have two we have two tables here because this one is for the chip components which are larger than 0603, and this table which is down here is for these capacitors and resistors which are smaller than 0603. Okay, so for different size of the component you may want to adjust the size of these specific parameters like toe or heel. What I would like to point out in these tables are the three columns which are here. We were not speaking about these columns yet, so I would like to play a little bit from our call where we were speaking about these different kind of densities, so everyone understand what are these columns, three different columns about. Maximum or most density, level A, then median or nominal density, level B, and minimum least density, level C. So okay, let's have a look what are these three different levels about.
And here talks about the three-tier density levels of IPC. Okay, I want to visually show you the least, the nominal, and the most. You see, the least has the smallest pad size, and the most has the biggest pad size. Okay, and there's this big pad size that didn't really swing it with the world of electronics. Okay, there's too much solder. The most is they call it very robust, but guess what? Very robust is it's too much.
And I wanted to know more. I wanted to know which of these densities I should use for the boards what I design. What are the differences between these densities? So we discussed this topic a little bit more, and this is from the first call what I had with the Tom, and on the screen you can see the software what Tom or his company they designed this software which can calculate the values for the paths, and these values are calculated based on the component dimensions and based on some recommended heel and toe and side values. Okay, so this software can calculate the path size But for now, we are not going to speak about this software. I wanted to mention it because you will see it on the screen when we will be speaking about these different kind of densities. So, very simple question. Why there are three different densities?
Well, you can have say terminal here, density level. I can say most here, and it gives me a bigger toe, and a bigger heel, and a bigger side fillet. Okay, and that's primarily, I would say, for the highest amount of solder volume that you could put on a pattern of maybe military weapons.
Okay.
Or maybe satellites,
For military applications, you mean, yeah. Doesn't have to be weapons.
Weapons in space, and maybe medical even. Maybe medical where you can't fail.
So it's reliability.
Reliability.
Yeah,
right.
okay.
Right. Okay, reliability. And then when you have your least land pattern, okay, it has your smallest toe, your smallest heel, your smallest side, and your smallest courtyard or whatever for packing densities or whatever. Now, this is for cellular phones or handheld devices. This is for the highest packing density. So you want to use the least amount of solder, the least amount of pads, so your pad size is very small. Okay?
But you go into risk that they are not so durable, yeah?
Well, no, we do it. We did test with the Japanese, and they they'd made test boards, and they said that, guess what? If I make a board with a board with an SOIC or whatever kind of a quad flat pack or whatever you want, and I'm going to use the most density level, okay, and then I'm going to run it through all these stress tests, vibration, thermal cycling, then I'm going to create another board with a nominal density level, and I'm going to run it through the same tests. They got the same results.
Okay.
So the most density level and the nominal density level did not produce any better results. Okay. So Dieter Bergman went over to Japan and found this out, and he came back and gave a webcast and said, guess what? We need to remove the most density level from IPC 7351, from the standard because the Japanese are telling me that the most density level doesn't do anything to hold the parts securely to the board over nominal. Nominal is just as good as most, okay? But Karen McConnell, the chairperson, she jumped in and said, well, wait a minute, Dieter, we just can't remove the most density level. It's got to have some use. And Dieter Bergman says, well, yeah, you're right. It could have only the use for hand soldering boards. If you're gonna use your solder and your soldering iron in one hand, and you're gonna put your solder there, and you're gonna hand solder your boards, maybe you could use the most density level. And we're gonna go ahead and put in the 7351C that the most density level is strictly applicable for hand soldering.
Okay.
Okay. And then the nominal is the nominal density level is the big one. That's mostly widely used by most people. And then you have your analog designs, your RF circuitry. Well, guess what? The RF circuitry, those engineers, they're saying that the least amount of copper is best for us. So I want the rock bottom least amount of copper. I want it to be reliable. I want it to pass all my tests. But I want it to be so that I have the least amount of copper, because more copper means I'm going to get more radio frequency, problems, issues, okay, in my circuitry. So they go down to the least density level. This is for RF and analog circuitry, okay, and cellular phones and handheld devices. So they can still, I mean, come on, if you drop your phone and it breaks,
display
are
will
they going
break.
to go in there and are they going to rework it? No. There's no such thing as reworking a phone if you have a cell phone, right? So if you have anything that's handheld, like a handheld mouse for a computer, and you drop it, if you drop your laptop computer, or if you drop anything, if you drop your backup drive and it breaks, you drop your little pad, your little your notebook pad or whatever, you drop it. Okay, if you drop it, it breaks. Okay, you're not going to send it back to the factory and have them say, fix it for me. You're going to throw it in the trash and you're going to buy a new one.
Yeah.
Okay, and so that's what the lease library is all about. Okay, so the lease library, it gives you the most bang for the buck as far as the most parts on the board in the smallest package possible, in the smallest container possible. And if you drop it and break it, you just toss it and buy another one.
Okay. So it may not be the best solution for industrial applications?
Well, it has passed all the tests. Okay.
Perfect. So now we know what these three columns means, what are the differences, and we should know how to create footprints, yeah? It's not so simple. So in the next clip, Tom is going to discuss the values, what you can see in these tables, the values which are recommended by these standards. And basically what they found out, maybe you may want to adjust these values because of a couple of reasons. So let's hear or let's watch the short clip.
I also want to point out that that the increments between maximum and minimum and medium is in 0.2 millimeter increments. And the feedback that we've gotten from our customers is that that's too wide of a range for, it's too much solder. If I have an 0603, which is a very small resistor, very short height, and if I have a 0.55 toe, that's a lot of solder out there. Mm-hmm. And if you go to the oven, if you go to the reflow oven, and it hits one pad, pin 1 and pin 2. Let's say that the oven hits pin 1 first, and you have all that solder on there, 0.5 millimeter solder. The part's going to flip up on its end. It'll automatically flip up, called this tombstone, okay? And because all the solder heated up on one side first, and it melted on pin 1 first, and then it pulled the part up. And so when it got to pin 2, the part was standing up, called tombstoning, okay? And so we don't think that this standard here really, because this standard is 10 years old, and this was produced before the 0201.
Now, I'm really confused. So, what kind of values I should use when I'm designing the footprint? And that's what Tom is going to speak about in the next clip. Basically, based on the experience, based on feedback, based on tests, based on these standards, they created number of different tables for different kind of components and for different sizes of components. And in these tables, they adjusted these parameters like toe or heel. They adjusted these values for different density levels and for different component sizes. So let's have a look on the next clip.
We said that that every chip from 01005 to 0201 to 0402 to 0603 to, they should all have their own. They should all have their own toe and heel, okay? So a nominal density for the 01005 is 0.005. For an 0201 is 0.1. But then for an 0402 is 0.2. Mm-hmm. Why does it double? Because the size of the part doubles. Mm-hmm. An 0402 is twice as big as an 0201. And therefore the toe solder joint goal has to double along with it, okay? Then the 0603 is just slightly bigger than the 0402, and we jump up again. Then the 1206. Now, see the 1206 now, we're at the 0.35. That's where IPC recommends. Mm-hmm. See, IPC recommends a 0.35, but then again, for an 1812 and a 12, the bigger the parts, we go bigger toes, okay, for the nominal density. So what PCB Libraries is saying, and we get this information from our customers, okay, that every single chip size should have its own solder joint goals. There should be no carte blanche blanket thing that say the toe value for all chips should be the same.
Now we should fully understand what is in this table. We know about these different density levels. We know what tau means, so it is this distance here. The heel is the distance here. Side is the distance between the edge of the component and edge of the path. And courtyard is the area which is around the component. This is the area which is needed to safely fit the component. Based on this, it should be quite simple to create any kind of path for these resistors, capacitors, for these cheap components. Just maybe the tricky thing about this is to remember all these numbers. And to make the life easier, as I mentioned before, Tom and his company, they created this kind of calculator or software which automatically integrates these numbers, tau, heels, for different kind of components, and you just put there the size of the component, size of the path, and the calculator or the software will automatically calculate the right path size. So let's have a look on this software.
Here is the nominal. See this white rectangle here is the nominal terminal, okay? And now I have no side and no heel, okay? But I have a toe out here, and the toe is right here, and the toe is 0.35 millimeter. So let me take the toe off, okay? And here, and now my pad size is equal to the lead size. So the pad is equal to the lead, okay? And that's what we start off with. So whenever we're going to generate a pad, we said, okay, well, what's the nominal lead? And what's the nominal, then make the pad size the same size, okay, X and Y, okay? And then we add the toe, heel, and side values right here, okay? And then we add the fabrication and assembly tolerance.
Wait, what? Tolerance? Okay, so to make it not so simple, now it is really simple to create new path. So to make it not so simple, you actually need to also count with some tolerances. When these components are created, they have some tolerances in the length and width, also even the contacts, they have some tolerances. And then you need to also count with tolerances during assembly and also with tolerances for PCB manufacturing. So to actually create a good footprint, you should include all these kind of parameters into the footprint. So not only the toe, heel, and side, but also all the tolerances. And I'm going to play again a little bit from this software because Tom nicely explains in this software how these tolerances influence size of the footprint. Now please don't take this video as advertisement for this software. That's not the reason why I'm creating this video, and I'm not paid for advertising this software. I just think this is a really great way how to explain what everything influence creating the nice footprint. So let's have a look at the next clip.
So I'm going to show you here how this affects the pad size. I'm going to eliminate the tolerance here. I'm going to change it to 0, and I'm going to make this tolerance 0 and this tolerance 0 here for the terminal lead, and then click on the OK button to redevelop. I'm going to recalculate the pad size, and so all the pad sizes are recalculated now. And I'm using only the nominal component dimensions. Now the reason why we include the tolerances for the package is because if in case the manufacturer, the component manufacturer, either for the component, is AVX or Vishay or Yageo, okay, Panasonic, if they produce a chip in the minimum material condition, I want that part, I want to be able to use it, and I want to be able to have a pattern that will be acceptable for that part to use. But if Panasonic or any one of them the manufacturers created a maximum material part in their tolerances, I want my pattern to be big enough to handle that part too. So I use the component tolerances, okay, to create a pattern that can accept the minimum material condition and the maximum material condition and the nominal material condition without any problems, okay? And so that's the reason for those tolerances in there, okay? Otherwise, if there wasn't, but in the future though, my vision in the future, and I'm looking out, way down into the land of 2035 or whatever, there might not be any tolerances. The manufacturing equipment will be so accurate that there'll be no such thing as tolerances, okay? That whatever the dimensions they call out will be the dimensions that they deliver. And any part that falls short or of that will be discarded. And they will only deliver component manufacturers will only deliver parts that fall in the nominal category. If some kind of inspection equipment, all these parts are going down the assembly line. They have optical inspection, and an inspector finds a part that does not meet this dimensional specification. They knock it off the assembly line. Okay, so in the future, all the parts there'll be no such thing as tolerances. So that'll be good. It'll be good for us because we don't have to worry about all the tolerances then. Okay, now I want to mention the manufacturing tolerance here, and I'll show you a picture of the image of the manufacturing tolerance about why it's important or whatever, and the assembly tolerance. Okay, I have a slide that shows that, but that's going back to the PowerPoint slide. But I'm going to go type in 0 here for the fabrication tolerance and 0 here for the assembly tolerance, and select OK. And now the pad size changes again. And now the only thing that I have left is the toe, heel, and side. Well, the heel is 0 and the toe is 0. So if I take the toe value away and change it to 0, now the pad size is 1-to-1 scale of the nominal the nominal lead. Okay, so I have a 1-to-1 pad. The pad is the same size as the nominal lead.
What I really like about this software is, as I said before, it will automatically fill up all these values. So even if you have no idea what kind of toe or heel or tolerances you should use, this software or the default preferences of the software will set it up the best as is recommended. But if you need to use different values, if you would like to adjust your footprint, you always can go into this specific settings for this specific component, and you can rewrite these values. I think it's really good, and what I really like about this software, I don't use it in my company, but what I really like and what I think could be beneficial in bigger companies and bigger teams is that basically everyone in the team will be creating components or footprints based on same standards. So multiple people can create footprints which are following same rules, and I think this can be really beneficial for bigger librarian teams. Now let's move ahead, and we are going to have a look on different kind of components, on the components what have the proper legs. Okay, so here is another clip.
The J lead component lead, okay? Because the J lead is where all your quad flat packs and your SOICs and your SOT 23s and all your other, your D-pack, your voltage regulators. There's lots of parts on the board. This is the next class down, the Goldwing lead. And guess what? They have information in J standard for heel, and they're telling you all about heel, the F dimension. They're really focused on the F dimension for the heel, but they have no information on the toe, none whatsoever. Okay, and so they even say in the picture on the left that the B dimension, the actual metallization of the lead frame can hang over the pad. It's acceptable as long as it doesn't violate the minimum electrical clearance. So the minimal electrical clearance is set by the trace space. So if you have a trace in a space and you have a solder mask and everything else or whatever, okay, you don't want to violate that electrical clearance. And so if your lead hangs off the pad, it can hang off the pad and it's okay as long as it doesn't violate the minimum electrical clearance. Okay, so therefore, in the world of land patterns, for tows, there doesn't really need to be one. Okay, because it doesn't make any difference to J Standard 001. Okay, they don't have any information on any tables. They're really concerned about the fillet of the heel. Okay, because that's where 70% of the entire strength of the solder joint is going to be. It's going to be in the heel. Okay, then the other 25% is going to be underneath the lead. Okay, and then only 5% of the solder joint strength is going to be out of the toe.
Mm-hmm.
Very, very little. It's insignificant. Okay, and so I'm going to change the slide again to go into what we determined. Okay, because here is the IPC 7351B table for the Goldwing leads. Okay, and they're saying that all Goldwing leads should be 0.35 millimeter nominal. And then if you're going to use the most density level, 0.55 most and 0.15 least, okay? And we got feedback from our customers saying that, Tom, you can't, the J Standard 001 says that there doesn't need to be a toe. But even if we did have a toe, we wouldn't want it any thicker than the C dimension. The C dimension is the terminal lead frame thickness. Okay, you see the C dimension over up here in the far left side. The C is the lead frame thickness, the terminal thickness. Okay, and so if I have let's see here, I'm going to move this down over here and back again. Okay, so if I have a 0.4 millimeter pin pitch part, the lead frame thickness on the 0.4 millimeter pitch is 0.15 millimeter. It's the nominal thickness of the lead frame. But as I go up to 0.5 millimeter pin pitch, the lead frame goes up to 0.2 millimeter, then 0.65 pitch is 0.25 millimeter, then 0.8 millimeter.
This table basically shows that for different thickness of the leg, you may want to use different toe, different size of toe. And you can have all the kind of different types of components. And you can have even like same type of the component but different number of pins. And these may have different pitch, different distance between the pins. And in this table you can see that basically components with smaller distance between the pins, with smaller pitch, they usually use thinner legs. And what Tom and his team, what they created are tables for all the kind of different components, and they specified these recommended values for the toe and heels, and all these values they specified for all these kind of different components. And that's what is going to be in the next clip.
And so now we have it broken down into SOP, QFT, and SOTs, and DPACs, and SODs. So it's all broken down by component family, because the DPACs have really thick metal. The Goldwing lead for a DPAC is 0.65 millimeter to 0.7 millimeter on the average. Okay, and it's way different than a 0.4 millimeter SOP, which is only 0.15 millimeter. Okay, so there's a big difference between 0.15 millimeter and 0.65 millimeter. The difference is a half a millimeter in thickness. Okay, and so therefore the toe on a DPAC needs to be much more robust than the toe of a 0.4 millimeter SOP. But again, the J standard doesn't have very much information about the toe on anything. Okay, but what we're saying is that, well, you probably should have some kind of toe out there, because my main concern is that if the toe is too big, okay, it's a waste of board real estate, number one. But most importantly of all, if the toe is too big, when you go to the reflow oven, the SOIC, the SOP, can float side to side on that toe. You see, when you go to the oven, it goes to this high temperature reflow oven, and the solder melts, and all of a sudden the part becomes fluid. and it could float on this solder back and forth, okay? And if the longer the toe, the more the distance the part can float back and forth. And so what I'm trying to do is to hold the part down so it doesn't move by shrinking the toe down to a reasonable level to stop the movement going through the oven.
And when we were speaking about soldering, I was curious to know what would be the path size difference if wave soldering is used or reflow soldering is used. You know, wave soldering is when you put tin on the PCB, and reflow soldering is when you just put your PCB into oven. Okay, so I wanted to know how this soldering process influence the path size, and here is the answer.
Well, that's because I brought this up to IPC way back in 1999 when wave soldering was really big. You know, they wave soldered the whole board or whatever, and the consensus was from IPC that wave soldering land patterns and reflow soldering land patterns made no difference. There was no difference in the results. Now some people differ with that. They said that, well, the side should be smaller and the toe should be longer for the wave or whatever. But IPC has no conclusive proof that the same land pattern can't be used for both processes for soldering.
The next question, what I really wanted to ask, was about path shape. I really wanted to know what is it all about these rounded corners or oblong paths or rectangular path which I should use in my boards. Am I doing wrong if I use rectangular path, or what are the benefits of rounding the corners on the path? So in the next clip, Tom is going to explain.
The IPC, ever since the IPC SM782 back in 1987, which was a standard for 18 years, they showed in the text oblong pad shape. They didn't call it oblong, they called it full radius. Okay, and so but full radius means oblong. Okay, and but all the pictures in the SM782 were all rectangular, and so people who didn't read the text created rectangular pad shapes. And I believe that that's where the component manufacturers, they got a hold of the standard and they looked at all the pictures, and all the pictures had rectangles, and so they made all their recommended patterns but rectangles. Okay? And so even though the standard says oblong, the component manufacturers recommended rectangle pad shape. Now, what we recommend at PCB Libraries is the rounded rectangular pad shape, because if you have a rectangular pad shape and you give that data to the assembly shop and they make the stencil is the picture in the middle, okay? And the picture in the middle has rounded corners. Now we gave them rectangular pad data, but they're going to use a laser to cut out those apertures, and they make the corners round to make it so that it lifts up easier, so that, you know, when you lift the stencil up, okay, you squeegee on the paste, then the stencil has to come up, and you want it to release all the paste down onto the board. Okay, and if you have sharp corners, the paste has a tendency to stick in the sharp corners. Of course, it depends on the viscosity of the paste. If it's a thick paste or a thin paste, okay, they have different paste masks. There's a couple hundred of them out there. So, but people would have trouble with the paste sticking in the corners of the stencil, and so therefore they round the corners so that they get a better release. Okay, and so what we're saying in PCB Libraries is that, well, then why don't you make the pad shape the same as the stencil shape? Okay, and also let's take a picture on the right hand side where there's no solder on the corners of these parts. On the left side is lead solder, and on the right side is lead-free solder, and you got no solder going out to the edges of the parts. Okay, and so therefore, I wouldn't how could you recommend a rectangular pad shape when it's useless real estate anyway, when there's no solder going out there, okay? And so so I think that, you know, when the CAD vendors produced a rounded rectangular pad shape, they kind of made their marketing, this is good for lead-free solder. That's not true. All pad shapes are good for lead-free. Okay, there's no such thing as a rounded rectangle that's good for lead-free. Okay, the rectangle is good too, and the oblong is good too, and the D-shaped pad shape is good for lead-free too. There's no such thing as a lead-free pad. Okay, so I wanted to get that out there so that everybody knows that.
So it's perfectly fine. Just use rectangular pad shapes, and it's no problem.
Yeah. If the component manufacturer recommends it, you know, you can go ahead and use it, but you're still going to get rounded rectangular stencils, and you're still going to get no solder in the corners. But it's okay to use them.
Okay, but we need to say this is only for like very small dimensions when it actually is really visible. For bigger parts, it doesn't really matter.
Well, yeah, I'm going to go into that. I think I'm going to go into that here in the near future here about why you have to use rectangular pad shape in some cases. Okay.
Okay.
So let's go ahead and flip the slide here. In these parts right here, these are called DFN, called dual flat no lead parts. And then the bottom picture in the bottom right is an LGA, a land grid array. Okay. Now, if you're using these parts, you have to use a rectangular pad shape. You can't use a rounded rectangular at all because the pad is 1-to-1 scale of the lead. Okay, so because believe me, this part and this part here and up here, it might look big. Okay, but it's really only 1 millimeter by a half millimeter. It is so small. It's micro small, right? You could put 1,000 of them in the palm of your hand, okay? And therefore, the pad size and shape have to be very, very close to 1-to-1 scale of that component lead, okay? And you know, and the same thing with the land grid array. The land grid array is sort of like a BGA but with flat leads or whatever, and the pad size is almost 1-to-1 scale of the terminal lead. Okay, and so for these component families here, you have to use a rectangular pad. So you have to know when to use an oblong pad, when to use a rounded rectangular pad, when to use a rectangle pad. You know, designers have to know, and librarians and managers have to know when these pad shapes come into play. Okay?
So can we say like it is safer to use than a rectangular pad shape always? You are not going to do anything wrong if you always use rectangular pad shape.
You're not doing anything wrong.
Okay, we know a lot about these standard pads, but what about the exposed pad, about the thermal pads, which are usually on the bottom of chips? And you can guess? That's what we are going to talk about in the next clip.
We're gonna talk about land patterns for thermal pads.
Okay.
Because thermal pads seem to be in most parts nowadays, where the only reason is because the parts are getting hotter and hotter. These semiconductors are getting hot. Okay, because there's a lot of processors in these. The more processing power you put in a semiconductor, the faster the speeds, and the faster the speed, the hotter the part. And they have to have a mechanism of reducing the heat of the part, reducing the heat away from the part. Okay, and so they put a thermal pad on there, but then the designer has to be very conscientious about where they put the paste mask. The paste mask is like IPC 7. The IPC standards say the minimum paste mask should be 40%, and the maximum should be 60%. But we use 50%, but we allow the user to change it. But we have rules.
When you say this percent, we are speaking about exposed pad, about the thermal pads. It is not for standard pad. Standard pad is 100%.
Standard parts, the leads are 100%.
Oh, yeah.
The thermal pads are reduced.
Okay.
By 50% or 60%. Okay. And that's because if you put 100% of solder on the thermal pad, the part will literally, there's nowhere for that solder to go. Number one, there's nowhere for it to move. Okay. And the part will float on top of that solder. Could you imagine that? Could you imagine having a full paste on a thermal pad and then going through the reflow oven and the parts floating on that thermal pad? Okay. What will happen would be the part, and this particular part here, the part would teeter-totter, and it would teeter-totter against the thermal pad, and then the leads, the other leads, pin 1, pin 2, and pin 3, and pin 4, would not make any contact with the part. There would be a little gap in between the pattern and the part, because the part would tilt because there'd be too much solder on the thermal pad. So we reduce the solder on the thermal pad so it can flow to reduce the thickness of the solder so the part can lay flat on the board. Okay, and these are the rules for the paste mask. You shouldn't put paste masks. You should have always a point, and when I say minimum, I mean minimum, okay? So you should have a 0.2 millimeter minimum between the signal pad paste mask and the thermal pad paste mask. And you should have a 0.2 millimeter in between, because don't forget, these are webs in a stencil. And you don't want to go less than 0.2 millimeters on a web of a stencil.
It's hard to
manufacture. The stencil to last
then,
longer. Yeah, well, if you only have a 0.1 millimeter web, the stencil is not going to last very long.
Yeah.
Okay. So you want, this is minimum too, by the way. You can go ahead and make your spaces in between these apertures of 0.3 millimeter, 0.4 millimeter, 0.5 millimeter. This is minimum. Okay, very minimum. And then from the edge of the thermal pad to the paste mask is 0.1 millimeter. Okay. And so you just have a 0.1 millimeter pull-in from the sides. I'm going to change the slide. So now IPC is producing a new standard called 7093 that targets in these thermal pads. Okay, and what they're saying is that that they're recommending a solder mask defined thermal pad. Okay,
that's
where
interesting.
You actually put solder mask over the part where you see the pattern. This is the pattern of the pattern here. Well, that's the solder mask pattern.
Okay, so that will be like 100% solder mask of this specific area.
Well, no. The solder mask you see here is the green. The green is solder mask.
Sorry, the paste would be 100% of this uncovered area on the exposed part.
Exactly. And then when you solder mask define your vias, because you have to have the via holes, right? Because the vias have to go to the ground plane to dissipate the heat. Okay, and so when you're dissipating heat, and you don't have any solder mask dams around those vias, and you have your paste mask when it melts, it's going to go down the via hole. And so what a lot of companies do is they have to tell their manufacturer to plug the via holes, and guess what? The board prices go up 10%.
But
so whatever
from my experience, if the hole in the vias is small enough, the solder will not go too much in. Or what is your experience?
It will not go all the way through the board.
Yeah.
Okay. If the hole is small enough, the solder will go down the hole, about halfway down the hole, and then actually freeze up.
That's almost everything what I wanted to ask about pads. There is one more thing what I wanted to know, and it's about this kind of exposed pad. In some chips, they use this kind of exposed pad when they cut off piece of corner, and in some data sheets they recommend the length pattern, or they recommend the footprint with exposed pad and with this corner cut off. And it's quite difficult to create this kind of special pad in the footprint. So I wanted to know if it's really necessary to consider this cut off corner in the footprints. And this is what Tom explained. So
No, I've looked at hundreds of data sheets, okay, where they cut the corner of the lead of the thermal pad terminal lead, okay, but then the recommended pattern has no cut in it.
Okay.
Okay. It's like, you have to look at the manufacturer's recommended pattern, and if the manufacturer recommends a rectangular pad, and even though they cut the corner of it doesn't make any difference.
Okay, so it's just to show where pin number 1 is, for example. It's
just basically to show where pin 1. It's a polarity marking for pin 1.
This is a good topic. So what shall we do if chip manufacturer recommends different footprint as the standard is saying? Which one we should use? Should we use the footprint which is following the IPC standards, or shall we use the footprint which is recommended by the chip manufacturer? I asked Tom. Here it is.
I would personally, there are certain component families, like for instance oscillators, corner concave oscillators, and side concave oscillators, and there are the bottom only terminal parts like the QFN and the SON. Let's go ahead here and open up an SON here. No, we're going to go with the QFN with the tab. Okay, so I'm going to look here, QFN with the tab, fill in some numbers. Okay, now here is the IPC math, okay, per their recommended toe heel inside, okay. But let's go ahead and I'm going to go ahead and take the I'm going to take the values away for the thermal pad there. Now for the manufacturer footprint here, I would say that linear technologies, I know what analog devices and linear technologies, I know what they do all the time for their recommended patterns. For these QFNs, IPC calculates a 3 millimeter spacing in between the pads, but linear puts it at 3.2. Okay, I know that. Okay, on all their parts, and then 4.2 over here. Okay, then they round this number here down to 0.7 and down to 0.25 or whatever. They have all kind of like nice numbers, and they click on OK, and this would be the manufacturer's recommended pattern. Mm-hmm. Okay. For linear technologies or for analog devices, okay, and I would probably go with their recommendation because they make reference designs, so they got to make a reference design of this part, okay, and they got to proof out the circuit somehow. They got to put their chip on a board, then they got to run their board through all kinds of stress tests, thermal shock, thermal cycling. They got to do stress tests, vibration tests. Okay, they got to run all these tests, and from these tests, they got to figure out, okay, what is the best land pattern, or what is the best pattern that we should use? Because if I create this pattern, they might create a board with 50 different patterns on it, and then they're going to populate the same part, the same package on these 50 different patterns, and the patterns are all designed by their internal engineering team. They have these component manufacturers have component engineers that are testing land patterns, and they might and each engineer will come up with a different pattern, and one engineer might come up with 2 or 3 patterns, and they'll put all these patterns on and put in a circuit board, manufacture the board, assemble the board, and then take that board through thermocycling, hot for 5 minutes, and then cold for 10 minutes, and then shake it up, vibrate it, maybe they'll put some G-forces on it, and then the parts will stop popping off the boards. And then the last part on the board, they could say, who designed that land pattern? Oh, Joe did over there. Well, that's the land pattern that we're going to use for our recommended pattern, because it's the last part on the board. It passed all the stress tests, all the cycling, thermal, and everything else. That part that's the golden pattern.
Wow. Do they really do this?
Yes, they do. A lot of manufacturers do. A lot of manufacturers don't. Okay, but I would say that the good manufacturers like Texas Instruments, okay, maybe Infineon Technologies. There are some, and maybe they don't do it to all their product line. Maybe they only do it to their new packages. You know what I mean? But we prefer to use the manufacturer recommended pattern. And on pod we have 2 million parts. And whenever the manufacturer gives us a recommended pattern or whatever, then we put that pattern in the spec.
Okay, so if there is a recommended footprint by the chip manufacturer, maybe you should consider to use this in your designs. And that's exactly what I do. When I need to create a footprint, the first place where I have a look is datasheet. And if there is a recommended footprint in the datasheet, that's what I use on my board. But be careful, okay? Sometimes there may be some exceptions, and that's what we are going to talk about in the next clip.
And you can see here that the manufacturer, the metallization of the terminal lead is there where there's a minimal amount of toe. Okay. Now, let's take a look at the data sheet for this guy. See here. So we're going to open up this data sheet here, and we'll go with the maximum width here, and then scroll down to where you see. So here we have, and you might lose my screen just for a second here, just while I get to this thing here. Okay, here is the actual part. Here's the
I remember this footprint. I had to make it actually longer because it was not possible to solder it by hand.
Right, exactly right. So here's the H dimension here. H, right? The overall from lead frame to lead frame, tip to tip to tip, right? And so the H dimension here is 6.2 millimeters maximum. Okay, you got min and max, right? So that's your dimension for H. Now, if you go down to the recommended land pattern, it says that the overall dimension from tip to tip for the land pattern is 6.2 also, 6.248. So how could you have your lead 6.2 and have your land pattern 6.2? This is a bad recommended pattern. Mm-hmm. Okay. And so basically then we go back to here and we say, go to footprint tab, uncheck the box and click on OK. And now we have this IPC pattern. Now, the thing about the IPC pattern would be that maybe, let's say that the A1 dimension is 0, okay, or 0.03 or something like that, okay. Okay, now I have that dimension there. Now I have a preference here that has a preference, and everything is built into preferences where you could just kind of like design your own library rules, okay? And so I'm going to say here that the minimum trim is 0.05 millimeter and select save that preference, okay? And then I'm going to select okay. Now see the pad here? It goes underneath the package. I'm going to get rid of the library editor here. You see the pad? It goes underneath the package.
Yeah.
Okay. Now, the package is only 0.03 millimeter standoff, okay? That means that when you place the part on the solder paste, and you go to the reflow oven, the part's going to settle down into the paste, and it's going to possibly, the bottom of the plastic bottom of the part is going to touch that pad,
yeah,
okay? And you're going to get solder all over the bottom of the part,
mm-hmm.
okay? And so let's trim the pads from going underneath the part. Select the OK button here. Oh, let me see here. I want to say I'm going to reopen up the part. Reopen up the part. But now I got the linear pattern there. Now I'm going to uncheck it and select OK. And then wait, component. Oh, it's back here. Let me change this to 0.03 again. When I reopen the part, see now we trim the pads from going underneath the part. So if your part is a low profile, now IPC didn't think about this way back in the 1980s because underneath the part they had to use this clean flux. They had to have this cleaning process, okay, to clean all the flux off the board. And so they took the finished assembled board and they would clean it through a cleaning process. But now the height is very important, okay, and so the height of the part you can control the height by simply controlling the thickness of the part, but also by placing the part smack dab on the board, making it 0, 0, making the standoff 0, 0. And that's the way most SOT23s are today. The standoff height is almost 0, 0, 0, okay? So therefore, you don't want to have your pad, your IPC, your heel going all the way underneath the part. And that's what Randy was complaining about in an email there. He was complaining about, Randy Clemens was complaining about another part here in one of his emails here. That was this part mm-hmm. here. he was saying, Tom, the Goldwing lead is too close to the body, and the pad is going underneath the part, and it's zero. There's zero, height, standoff height, and so my plastic is going to touch that pad with solder on it. Okay, and so I can't have this. And so that's when I told him about this trim pad feature.
We can't have it because it can, like, the solder may spread and cause some short circuits
yeah, if you're using a fine pitch part, like a 0.4 millimeter part or whatever, you could have solder bridging. We have no reports of solder bridging yet. Nobody has ever reported this, because what happens is that when your plastic touches the solder, it pushes the solder into the heel, up the side of the lead. Mm-hmm. So there's no solder bridging going on, because why? Because you have solder mask in between the pads. Okay. If you gang mask your solder, if you gang mask your whole row of pads, and you have no solder in between your pads, then you might experience solder bridging.
Okay. So basically, you recommend to follow the data sheets, but still be careful and check if it makes sense.
Yes, you have to have some kind of knowledge about, like I took the CIT certified, J Standard 001 class for 1 week or whatever, and I learned how to solder parts. I think every PCB designer should learn how to solder parts to boards.
Yeah.
Once you learn how to solder a part to a board, then you know what a good pattern from a bad pattern.
Yeah, I completely agree. Every hardware design engineer, even software design engineers, they should know how to solder properly. You may not believe, when I was starting with hardware design and my soldering was really bad, I spent a lot of time debugging boards with a fault because of my bad soldering. And then I just soldered a component properly and everything worked. Miracle. Yeah. And I would like to say, for good soldering, use a microscope. Once you solder under microscope, or if you inspect your soldering with a microscope or with some, something zoom in, then you will see if your soldering is good or not. And that will help you a lot. Just buy a good microscope. Now, I would like to speak about something a little bit different. Always when I'm designing footprints for a chip, or not always, but sometimes I had this question like, do I need to use local fiducials? Maybe you have seen this on some boards close to chip. There are local fiducials. And I don't really use this on my boards, and I have never had any problems with this. But I always wanted to know if we should be placing these local fiducials into our libraries or not. So I had the opportunity to ask Tom, and here is the answer.
Local fiducials, this is in the IPC 782, okay? And they give you guidelines about where to put the local fiducials on, okay? But we used to do this in the 1980s and the 1990s or whatever. But today when we talk to assembly shops, they're saying, please leave the fiducials off. There's no need for them. Our pick and place accuracy, because the reason in the 1980s and the 1990s, why the reason for the local fiducials was because they would put the boards on a conveyor belt, go down the assembly line, okay, down the pick and place assembly. And then sometimes the board would become crooked a little bit. Maybe it wouldn't be totally aligned, straight vertical, okay? And they would have to take a bomb sight light and bomb sight the fiducial, and then bomb sight the other fiducial, and then register that information to get the center of the part. And then they would go to the pick and place machine and place that part per the fiducials, okay? Where now the accuracy of the pick and place machines is so accurate that they no longer need the fiducials.
Okay, I would like to add, I still can see these local fiducials on some large boards. Okay, so maybe it may you may want to consider some factors when you may want to use these local fiducials, but in most of the cases in standard small boards they may not really be necessary. And as you can see, we are slowly moving to BGAs. So in the next clips we are going to speak about BGAs, and we are going to start with some really nice pictures and explanation about collapsing and non-collapsing balls in the BGAs, and the solutions and the paths for these collapsing and non-collapsing BGAs.
Like you want a BGA to collapse around the pad, so you have to have here's your solder mask right here, your green solder mask, okay, and there's your pad is much smaller than the ball, okay. And when you go to the oven, you want the BGA to collapse all the way around the perimeter of the pad to grip that pad. So you pull the solder mask away, okay. But now the BGA pin pitch is getting smaller and smaller and smaller, okay? And then you get a BGA pad that's so small, okay, that if you take the BGA and you collapse the ball around the pad, and when you do a drop test, let's say you have a cellular phone or any kind of device where you hold in your hand and you drop it, okay, the solder joint maintains its strength because the ball is collapsed around the pad, okay. But the problem is that the pad detaches from the board, from the pre-preg material. So when you drop a handheld device and you go and open it up to see why did it fail, it was the pad that ripped away from the pre-preg. The blunt force.
Yeah, because they are so small that the weakest point is actually between the copper and the pre-preg.
Right. And so therefore, when you get to a really small pin pitch for your BGAs, and you got to do a via and pad, we recommend that you grow the pad a little bit bigger so you can't collapse around it. You don't collapse, okay? Because you have to put a via, a blind via or whatever kind of via in the pad, because you can't fan it out like normal, okay? And so you make your pad size bigger, as big as the ball, or if not bigger than the ball. Then you solder mask define it. Solder mask define would mean that you take the solder mask and you bring it over the pad a little bit by 0.05 millimeters, okay? Just bring the solder mask over the pad, and then when the ball melts, it's gonna create a good a solder joint on the pad. And when you go to the drop test, the solder mask will keep the pad held down to the pre-preg.
Mm-hmm.
Okay, so you're adding additional strength to the pre-preg pad combination.
This was quite interesting for me, and I searched for some pictures about collapsible and non-collapsible balls. So this is the picture what Tom had. It is from his company, PCB Libraries, and you can see also this picture. On this one you can nicely see the solder mask. It actually goes and covers the pad. On this picture the mask doesn't cover the pad, so we cannot see it here, but this is basically what is happening, okay? So on the collapsible balls, the tin goes on the side of the pad, and in non-collapsible balls, this side of the pad is not soldered. Ideally you would like to cover it with the mask, so it basically glues or it holds this very, very small pad a little bit stronger than if the copper would be just like this. What was interesting for me was also to know that there are different kind of balls, so different kind of material is used for different kind of balls, and for some balls they will just no collapse, and it not only depends on materials, but it also depends on the size of the ball. So even if you create the pad like this, that's what I understood, even if you create pad like this, the ball would just not collapse around these edges. And that's what we are going to speak about in the next video.
The balls, the non-collapsing balls, don't forget, a ball is made out of lead too, right? And don't forget, we're trying to get rid of lead, okay? So in order for a ball to melt and collapse, it has to be made out of some kind of soft material. And so when they make a ball out of tin, and maybe silver and copper, okay, the ball size becomes very hard, and it doesn't collapse.
Ah, okay.
But I've never seen a ball not collapse on a pin pitch greater than 0.65 millimeter. So whenever you can't start fanning out the BGA, and you have to solder mask define the pads, and you have to put the hole in the pad to get the annular ring in there, those pads are not going to collapse anyway. They're not going to go anywhere. IPC used to say all the time, you cannot solder mask define a pad, a BGA pad, and they were really adamant about this until Motorola contacted me and they said, Tom, IPC says don't solder mask define. Our manufacturing engineers say solder mask define. We got I want you to get Dieter Bergman on the phone. I want you to get IPC on the phone. I want to get my manufacturer on the phone. We need to talk about this. And then when the manufacturer engineers told Dieter Bergman that the stress test, the drop tests, okay, the vibration and the shock, when they drop a Motorola phone, okay, that the pad rips away from the prepreg, Dieter Bergman says, oh, I know what you're using the solder mask for. You're using the solder mask to hold the pad down to the prepreg. If you have to do that to pass your drop test, go for it. I'm so sorry that we said, don't solder mask. Solder mask defining a pad, a BGA pad, is wrong. It's bad. Don't do it. Don't ever do it. And Dieter Bergman changed his mind after talking to these people who actually do it. That's why we're saying that not everybody follows IPC, because IPC says some things that don't make any sense.
And this is exactly why I love to have these kind of calls and create these kind of videos, because I can learn the background behind some of the decisions, and then you understand better why you are doing some of the things. In the next clip, we are going to speak about this, or Tom is going to speak about these tables, what you can see here. So this first table is for collapsible solder balls. This table is for non-collapsing balls. Notice these columns which are here. So this is the ball diameter. Then here is the reduction. And as you could hear, for the collapsing or collapsible balls, we need to reduce the size of the pad from the ball size. So ball diameter is 0.75 millimeter. We need to reduce this by 25%, reduction by 25%. So the nominal pad size is 0.55 millimeter. But because of the variation, tolerances, or Tom will speak about this, you will get like this kind of range, 0.6, 0.5, and then you need to choose which one to use. As I say, Tom will explain, but I wanted to go through this table so you understand what is in these columns. For the non-collapsing balls, notice ball diameter is here. In this case, we are not going to reduce the size. So the pad size is not reduced from the ball diameter, it is actually increased. So the pad is going to be bigger than the ball. It's going to be, in this case, for the ball diameter 0.75, we will increase the size by 15%. So the pad is going to be 0.85 millimeters, 15% bigger than the ball diameter. Okay, let's play the video.
By the way, the ball size is normally 50% of the pitch. So if I have a 1 millimeter pitch part, the ball size is normally 0.5 millimeter okay,
Mm-hmm.
or somewhere in a range around that range, okay. So so now, let me see here. So now so here we have the reduction. So here we have the pad. See, so the ball, for a collapsing ball, the pad has to be smaller than the ball. It has to be smaller. In order for the ball to collapse around the pad has to be smaller. Okay. So here's all your reductions. So you reduce the ball by 25% in the beginning, but then once you get down to a 0.5 millimeter pad, it's 20% reduction. Then when you get down to a 0.2 millimeter ball, it's a 15% reduction. Okay. So that's how you figure it out. Now, once you get your reduction, you get your land variation. So here's your ball, here's your reduction. Then you got your pad size, 0.55, but a 0.55 pad has a plus or minus 0.05, so it could be a 0.5 or 0.6, okay, as a variation. And IPC, the reason why I bolded these numbers here is that IPC will always recommend to use the maximum material condition. So even though they're saying a 0.75 millimeter ball is a 0.55 millimeter pad, don't use the nominal pad size. Use the maximum pad size or the variation. Mm-hmm. Okay. So in our calculator, when you calculate so we get this question all the time. They're saying, well, I have a 0.6 millimeter ball, but the calculator is giving me a 0.45 millimeter land, even though it's a 25% reduction. Well, that's because IPC says use the maximum land variation of that pad. Okay. And that's the reason for that. Now, this gets kind of complicated because math isn't always easy to a lot of people, especially when you're doing 25%, 20%, 15% reductions, and then you've got your pad size, then you got your land variation, then you take your maximum land variation. Now, for the non-collapsing pads, okay, well, these are non-collapsing balls. These normally are the fine pitch parts, okay? They start at the 0.65 millimeter pitch where you cannot fan out a dog bone fan out, okay? You have to have a via in the middle of the pad, okay? For a 0.5 millimeter pitch BGA, for a 0.4 millimeter pitch BGA, all the way down to a 0.3 millimeter pitch BGA, you have to have a via in the pad to get down to the inner layers.
So, in a case, if you don't have any recommended footprint for a BGA, these are the two tables what can help you. But these tables are not really speaking about mask. We were not actually speaking about mask. You know, this usually green color on the PCB. So, how we should design or consider the mask in our footprint. And you can guess that's what the next clip is going to be about.
No, IPC says, and very clearly in the 7351, well, the mask is not a part of J Standard 001. There's no such thing as, they don't mention solder mask in J Standard 001, okay? But in IPC 7351, they say that the solder mask and the pad size should be 1-to-1 scale, and you should allow your printed circuit board manufacturers to adjust the swelling of the solder mask per their tolerances.
Okay.
One manufacturer will have a 2 mil or 0.05 millimeter tolerance. One will have a 3 mil 0.075 millimeter tolerance. You know what I mean? Different manufacturers will have different tolerances, and so whatever. See, the whole goal is that you don't want your pad to be underneath the solder mask. You want your pad to be fully exposed for your solder, okay? And you know, and so that's the reason for swelling it. The only reason why we're swelling the solder mask is so that to give the PC fabrication shop a little bit of tolerance for their solder mask application.
They have been doing this construction work for whole time I've been recording these videos, and I had to re-record so many videos because of these noises. And you know what is really interesting? they always start drilling when I start recording the videos. When I answering emails, then they are quiet. But when I hit record, they start drilling. Okay, let's go back to our topic. We were speaking about mask, and even if theoretically you don't have to specify anything special about mask, so theoretically mask could be 1 to 1 comparing to part size, and the PCB manufacturer would apply their tolerances and PCB and manufacturing capabilities, and they would make the opening a little bit bigger. When I'm creating footprints, I always create the mask opening a little bit bigger than the part, because I would like to see how it is going to look on real board. Yeah, especially I'm very interested to see if there will be these slivers or the separation between parts which are too close to each other. So normally I use 0.1 millimeter bigger opening than the part. So this is the part. Here this is 0.1 millimeter. This is the opening in the mask. And in some cases I use smaller numbers, for example 0.075, like 3 mils, or sometimes even smaller numbers. But you need to be very careful, because some PC manufacturers may not be able to actually create so small gap between part and the mask opening, because of, they don't have so precise machines, so they will make the opening bigger anyway. But there are other reasons why you would like to see this mask opening during your design process when you are creating the board, and one of the reasons is mentioned in the next clip. So let's have a look.
Okay, now we're talking about solder mask, okay, here, and we're talking about legend, okay, silkscreen legend. The reason why we don't call it really silkscreen anymore is because silkscreen is a process, okay. Silkscreen is like a physical process where you have a screen and you have some paint and you have a squeegee and you squeegee the ink onto the screen, and that's called silkscreening, okay. The actual name of these markings, which they now apply on the printed circuit board using an inkjet printer, is called legend, okay? So whenever I have legend over solder mask, you see I have a pad, okay? So I have a pad right here, and then I have my solder mask swell, okay? And then I have a legend designator on top of the solder mask. The manufacturer, the PC board fabrication shop, does not like legend in non-solder mask areas, okay? So that what they will do is they will superimpose the legend layer and the solder mask layer together, and they will trim all the legend away from the solder mask. And they'll even actually amplify the solder mask a little bit more than they need, and trim it even more. Because don't forget, there's a registration tolerance to applying legend, and there's a registration tolerance in applying mask. And they don't want to get the registration tolerance with the mask and the legend mixed up, where the legend happens to fall inside the mask. So they want to compensate for all their manufacturing tolerances and get that legend as far away from the mask as possible. And so they'll swell the mask a little bit larger than necessary and then trim the silkscreen. And so this is what you're going to get. This is exactly what you're going to get. You're going to get your U is going to turn into an II, and your 5 is going to get trimmed in the bottom, and your 3 is going to get trimmed in the corner here. And that's what you're going to get on your silkscreen legend.
So always when you finish your PCB, don't forget to check your mask layer and silkscreen layer together. So you are sure the silkscreen layer is going to look as you would expect, or the legend is going to look as you would like to have it. And when we are speaking about this legend layer or silkscreen, I wanted to know a little bit more about the pin 1 marking, because I found Tom's presentation on internet with some new suggested changes in the standard, and one of the suggested changes in the new standards was how this pin 1 is going to be marked, and this is the suggestion. And I wanted to know what is behind of this suggestion, and also I wanted to know what is actually the right way how the pin 1 should be marked on the silkscreen or on the legend, and also how it should be properly marked in the assembly drawing layer. And in the next video you will see what we were talking about.
That we have, we're talking about polarity marking, okay? And you said something about, you asked me a question before about lines versus dots versus, what can we use for these polarity markings, okay? And over on the far left picture is a line right along pin 1, okay? And the reason for the line was because we thought, well, if we get to use the line, it's very, very visible, see the entire length of the pad, and it's inside the courtyard. You have a placement courtyard, and look at the dots. The dots in the 2 pictures there are outside the courtyard, okay? So therefore, you cannot place parts on legend. If you put the dot in your library and you put your library on the board, you can't put a part in that dot, right?
It takes unnecessary space.
Yes.
And for today's electronic, it may be a lot. You can put there a component.
Right, and then what you might want to do is you could, I mean, if I could, I would actually take the dot and put it there, and I would take the courtyard and I would stretch the courtyard. I would take the courtyard and stretch it around the dot. You know what I mean?
Yeah, I understand.
A courtyard is a keep out area for the thing. Okay. So anyway, so this is about legend. Legend polarity. Okay. I could go to our program and show you all about legend polarities, but the shape of the marker, whether it's a triangle or whether it's a dot or whether it's a square, is totally up to the user, okay? And because everybody is different strokes for different folks. I think the triangle is very, very popular in Europe, okay? The dot's very popular here in America, okay? We introduced the line, but I don't know who uses it. I don't know, but we wanted to get people the option of lots of options. I'm going to go to the next slide, and we're going to talk about assembly polarity. The assembly polarity, you could either use a chamfered line, a chamfered polygon to indicate where pin 1 is, or a rectangular polygon with a dot. And they're both the same. I mean, they're not different. I mean, I think that maybe the one on the left is easier to print and it's less data that you have to store. Could you imagine having thousands and thousands of parts in your libraries with big dots in every single part, okay, for your assembly, and your library is probably going to be bigger in size, for your hard drive or your solid state drive or whatever. Your library is going to be bigger. So the more features you put in this thing, now having a chamfered line, we're just trying to lighten the load a little bit here, lighten the library load up, okay? But again, though, if I go to the next slide here, this is the polarity marking for a legend and an assembly for a connector, because connectors have this triangulated image imprinted in the plastic of the connector. They have a little triangle in the connector, okay, in the plastic. And so then we put a triangle for the assembly drawing on the connectors, and then we put a dot outside by pin 1. We put it now, we try to get it as close as we can inside the courtyard, and we get it as close as we can, but there's rules. A 0.2 millimeter this way and a 0.2 millimeter that way or whatever. Keep it away from this, keep it away from that. Don't get it too close. If you get the silkscreen legend outlines too close to each other, they could melt into each other where they merge together. Then you can't tell what it is, the features, okay? So you have to have a little bit of space in between your legend features in order for you to identify what they are, okay? And the only reason for the dot anyway is to keep the assembly shop honest. Because you could have a diode that requires polarity or whatever. You could have any SOIC requires polarity. You can't invert an SOIC. You can't invert a quad flat pack, or you can't invert many parts on the board. You can't invert a resistor. You can invert a non-polarized capacitor, but you can't invert an SOIC, okay? And if you do, it won't work. So therefore, and the SOICs are clearly stamped in the plastic where pin 1 is. And so when you get the board, the assembled boards back from the shop, you look at your board and you look at all your legend dots to make sure that they're matched up with all the component dots. And if you see a legend dot on this side and the component dot on that side, way over there somewhere, then the part was inverted accidentally by the assembly.
I know exactly what Tom is talking about, because I've seen so many boards with chips fitted the wrong way. So always when you receive a board, especially like very first prototype, the first thing what I really recommend and what I always do is visual inspection. And I have a look if the component pin 1 is correctly placed on the pin 1 location of the footprint. And that's why you really would like to have, or that is one of the reasons why you really would like to have visible pin 1 location on the footprint. In the next clip, we are going to speak about pin 1, but in your libraries. So when you create a library, when you are creating library and when you are creating footprint for a chip, where do you place pin 1? In our libraries, we place pin 1 in this top left corner. But I have seen in some libraries and in some documentation, they say place pin 1 this way, bottom left corner. So what is the right way? How should I create my libraries? Or am I doing wrong if I'm placing pin 1 in the top left corner? I asked Tom. Here is the answer.
And this is for the pin 1 orientation, because we have pin 1 identifiers, but then where should pin 1 be? Should it be in the upper left or lower left or whatever? Okay, and here's the tables for IPC 7351B, upper left. IEC said no. They created their standard for polarity for pin 1 orientation 2 years after IPC 7351B came out. 7351B came out in 2005. IEC 61188-7 came out in 2007, and they said lower left. And then you take a look at EIA, and they're kind of matching IEC, and Valor VPL is kind of matching IEC, and so therefore we match that, but we have it so that you can change it to any rotation that you want. But the whole idea behind the rotation was to automate the assembly process, because the assembly shop has to take your data and spend 8 hours up front trying to figure out where pin 1 is and what rotation did you use on your printed circuit board. What rotation did you use?
So what this table means for us? It means that, for example, if you decide to follow this kind of standard, that when you create a footprint for, I don't know, BGA, then you may want to place pin 1 into upper left corner. But if you decide that when you are creating libraries you are following this standard, then you may want to place BGA pin 1 into lower left corner. But in reality, I don't think the assembly house will blindly follow the standards. I don't believe that if you send your board into assembly house and you will tell them, when we were designing footprints, we follow this standard, so you can blindly trust all the footprint rotation or zero component orientation is based on this table. I'm quite sure they would check every single component before they would place it on the board. They would check the rotation of the component, because if they build thousands of boards with wrongly rotated component, it is usually their fault. Okay, and when we are speaking about these pins, what I was also curious to know about is what people say, or what standards say about this diode marking. If there is something about if we should use letters or numbers for the diodes or similar kind of components. I normally use numbers 1 and 2, but after I talked to Tom, I'm really considering maybe move to these C and A letters. When I was starting with hardware design, I was creating everything by myself, and now I know that more engineers may work on same project, and if more engineers are involved in design of one board, then it may be safer, in my opinion, it may be safer to use the letters. If you are alone, if you are designing the boards all by yourself, then you can use anything you want. You are not going to make any mistake because you will always double check everything. But if there are more people involved, maybe this C and A can be better way to go. But here is something from our discussion about this diode pin marking or pin naming.
For the polarity markings, we have a question about anode and cathode and diodes and pin 1 and pin 2, okay? And for cathode and anode, it's better to use the numbers, the letters C and A for cathode and anode, because if you use pin 1 and pin 2, the schematic symbol will be pin 1 and pin 2. And what happens if the engineer put pin 1 as the anode on the schematic symbol? Then they give you a net list, and then you have pin 1 as a cathode on your footprint. Then the manufacturer, everybody does their job and everybody does fine. You get the boards back and they don't work because the engineer had pin 1 on the anode, the designer had pin 1 on the cathode, and it's called a screw up. And so therefore, in order to not screw it up, you just use A and C, and it's impossible to screw up. Impossible.
Oh yeah. Once you know what you need to be careful about, then you will create the footprint perfectly fine. You will use the proper pin names, pin numbers. But you know, I remember the times when I was starting with hardware design, and most of the mistakes what I used to do were in the pin names or pin numbers of footprints. I think everyone who is starting with hardware design goes through this process, and everyone learns the hard way. Many people remember this. I really remember my mistakes. DB9 footprint, which was inverted. SOT transistor footprint, 1 to 3, 3 to 1, diode footprint. And yeah, we all learn from these mistakes. It's nothing special if something like this happened to you. All times. Let's go back to our topics so we can finish this video, because we are almost at the end of everything what I wanted to tell in this video. In this next clip, I would like to speak about, not about pin names, but about the footprint names. How I should call the footprints what I create. And in the next video, Tom will use the document from their website, from PCB libraries website, you need to log in, and then you will be able to download the document what he will be using in the video from here. Okay, this is the document what you can download, and in the next clip Tom will be speaking about what we can see in this document and how these names for the footprints can be created.
Now I'm going to log in. I go to downloads and I log in, and then here's all the documents right down here. Here's the footprint naming convention. Okay.
Okay.
So let's go ahead and grab it. Okay. We're going to grab it. Okay. This is for library expert, and then they have IPCB or whatever. They don't, because C doesn't exist, so we couldn't put C on there. So anyway, so I got the document here, and what we'll do is we'll scroll up really big so we can actually see it. And what this is the naming convention is broken down by first family. Okay, ball grid arrays, capacitors, diodes, crystals, ferrite beads. So you have your family first, okay, and your family for like a chip could be called RES for resistor, or CAP for capacitor, and IND for inductor. So you have your component family, and then you have your pin quantity. How many pins are in this part? And of course, for a 2-pin part, you don't ever put in 2 pins. It's 2 pins if it's a chip part or whatever. Then you have component dimensions. Here we start off with QFN in the beginning. QFN. Then the 29 means 29 total pins. We include 28 pins plus the thermal pad. Then the P stands for pitch. Pitch is 50. Comes from the pin pitch. Okay. Then we got the body length by body width by height. Then the lead, the nominal lead size, the nominal lead length, the nominal lead width, then the thermal pad length and the thermal pad width. Okay. And a lot of people are looking at this naming convention now, and they're saying this is too many characters. And one of the things that IPC is introducing with IPC 7351C is a JEDEC naming convention, which makes the names even longer. We're talking about a possibility of a 60 to 80 character footprint name using the JEDEC naming convention. It'll be really wild. Okay, so what we're defaulting back to, and we're going to be possibly introducing this feature in our 2020 software program, is the ability to use the manufacturer name abbreviation, like TI is the abbreviation for Texas Instruments. I would never want to have a library part named Texas Space Instruments. Okay. For one thing, spaces aren't allowed in library names, and number two, you'd have to put an underbar underneath there or whatever, or a dash. And Texas Instruments is way too long in itself, so you would use its abbreviation TI. And we have all the abbreviations for all the manufacturers. Okay, then you would use their case code or their part number. But that's on another slide down. I'm going to change slides now. I'm just saying this, that we're getting a lot of feedback from a lot of customers that the IPC 7351 name for footprints for LAN patterns is too long, and the names that they're going to work on right now are JEDEC, and they're even longer, and they don't make any sense hardly. You can't. They're very, very difficult to understand, the JEDEC naming convention or whatever. It's, you have to be almost a rocket scientist, or you have to have a little cheat sheet thing to know what each character in the name is. Okay, at least here, I mean, I'm used to this now. After years of this naming convention, I could look at a name and I know exactly all the dimensions of the part. I could look at the footprint name and I know all the dimensions. I know that it's 29 pins. It's a QFN. I know it has a 28 pins plus a thermal pad. I know it's 50 mil pitch. I know it's 5 millimeter by 4 millimeter by 0.8 millimeter height. I know it has a lead size, a nominal lead size of 4 millimeter, 0.4 millimeter, 0.25 millimeter. I know everything, right? So the name spells out all the dimensions in the part. So I could look at it and I could say, well, I can build that part. I can just take the name and then just reverse engineer it and build the part, fill in all the values. The only thing I don't know from the name are the tolerances. Okay, but as we shift gears here and change the naming convention here slide, this is a much better naming convention to our customers, where we use some kind of a abbreviated name like TI, okay, and then underscore, and then the case code. This case code might go with 1,000 different part numbers, but this is a case code. That's all it is. The case is a case, and it just has package dimensions or recommended pattern.
So that's basically the identification for specific package for this specific manufacturer.
Right. Now let me go in, like, for instance, for connectors, every connector is different, right? Every connector is different. I mean, you have you have an HDMI connector. It's totally different than a USB connector. You could have a connector for, all these different applications, but they all have different numbers. And the number of the connector, the number might include things like what metal the leads are made out of. Okay, it's all part of the number. Like here, I have a Molex 67503-1020, but 1030 might be a different metal for the lead, and 1040 might be a different metal for the lead. One might be tin, one might be lead, one might be copper, one might be gold plated, okay, tin plated, okay. So basically, do I need that information in my footprint name? No, not really. But that's the ordering number for the part. When I'm going to go buy the part, that's the number I'm going to use to go buy it. Okay, so we use the full part number for all connectors.
I do that.
And if I were to switch slides here, we have an abbreviation. See, over on the right hand side, we have all the abbreviations for all the. I would never have a footprint name called Advanced Acoustic Technology. Too many characters. It's ATT. AAT is the footprint name. Okay. Then I either use the part number or the case code. Now I always use the part number when it's a unique part, and only that part number is good for that one package. But if that package could be used with multiple part numbers, then I use the case code.
Mm-hmm.
So it's the manufacturer name _ the case code. A case code would be like 0603 is a case code.
Okay, and that's basically everything what I wanted to include in this video, specifically about footprints. But during the call, we discussed also a lot of other things. And one of the questions what I had, and what I think could be also, the answer could be interesting also for you, is who actually is the IPC? Because I had no idea. I know it's an organization, but what they are doing, why should I follow IPC? What is their purpose, how they work? So I asked Tom to tell me a little bit more about IPC, and here is Tom's answer.
No, that's a very interesting question, because IPC, well, they're not exactly, they're kind of like they're not a big organization. They have employees that take care of, trade shows, because trade shows is a really big thing for them. IPC Apex, they make a lot of money off these trade shows, where they rent out these conference centers, whatever, and they have all these printed circuit board fabrication equipment and assembly equipment, okay? And they charge, $10,000 for booth space, or I don't even know what the cost is for a booth space or whatever, but they've got to make a profit off of that, and then they manufacture these publications, these standards, okay? And in the standards for IPC, they have a liaison. So IPC will assign somebody, an employee of IPC, as the liaison, okay? And then they'll form a committee. And the committee will be like, let's say the land pattern committee, okay? In the land pattern committee, they'll put out a notification saying, we're going to start a land pattern committee. Anybody who wants to join can join, okay? And then so now we have 80 members joining the land pattern committee. And these are 80 people. These people are from all different companies. It could be Motorola or Raytheon or Boeing or Honeywell. They could be just volunteers who voluntarily look at the standard, and they want to, and maybe they're working behind their desk at their big company, and then maybe they have some suggestions or recommendations or whatever, and they have these conference, they have webcast meetings, and so the IPC liaison is simply there to take notes and to type everything down, and when people say, I want to change this to this, okay. So somebody on the subcommittee can say, well, this wording is not totally correct. You should word it like this or whatever. So IPC is kind of like a collector of knowledge. They go out and they say, we're going to have this committee for terms and definitions, and this committee for manufacturing, and this committee for assembly, and this committee for land patterns, and this committee for schematic symbols and whatever. And so they'll have all these different committees, and they'll go out and they'll find volunteers to participate. And all the volunteers, they give IPC all of their knowledge, their best knowledge. And a lot of the best people in the world don't join IPC standards, okay, specifically because they're going to lose their competitive edge. If you are a service bureau and you have all kinds of inventions that methodologies and things that you've developed that give you a competitive edge over your competitors, okay, you're not going to want to give this information to IPC so they could publish it to the whole world, okay? So IPC has these volunteers, but these volunteers aren't the best of the best in a lot of cases. Some of them are. Some people like me are very giving. When I join IPC, I give IPC everything that I could possibly think of and invent or whatever. I give it all to IPC so they could publish it and put it out in the standards. And there are people like me out there. But there's a lot of people not like me who want to hold on to their knowledge and their proprietary information, and their companies won't let them join IPC.
I understand, because I guess when we were speaking, for example, about testing these footprints, and it also cost a lot of money, the company to do all their own tests and come up with the best footprints or something, and they just keep it for themselves, I guess.
Yes, yeah. It's sort of like IPC. They can't adopt to any new technology. Like, let's say if I invent something new. Okay, I'm a new manufacturer, a component manufacturer, and I invent something new. You can't get that into IPC because it's not proven technology yet. Okay, IPC only puts in their standards data that's proven technology, that's been proven over and over and over again to work. And once it works, then they publicize it. They sell it. They sell the publication. They say, okay, well, we tried this, and we tried it on 100,000 different people or whatever, and everybody says it's okay.
And this was really good information, because before I knew these details about IPC, sometimes I've got scared. Yeah, when people say like, do you follow IPC? Do you know this IPC? Do you create footprints based on the IPC? And I was like, I don't really know much about IPC, but does it mean that the footprints or boards, what I design, are they wrong? Now it's clear. Okay, IPC is organization which groups number of different people and collects the information from these people, and based on this information they give some guidelines, or when we speak about these footprints, they give some guidelines or recommendations which will help you to do not make mistakes what other people did. So this IPC is to help you to create something without actually maybe going through the process of pain and discovering, oh, this is something what I did bad and next time I have to do it different way. Okay? But if you think you could hear this from Tom, there are a number of people what are actually not following, or a number of companies that are not following IPC standards, but they need to have some kind of proof or testing that the way what they are using or the way how they are doing their designs and boards, it's proper and high quality way to do it. Okay? So don't be scared when you hear someone speaking about IPC and you have no idea, or you had no idea. Now you will know what does it mean. But don't get scared when you hear someone speaking about IPC. Now, there is one more question what I really wanted to ask Tom, and it's about what he thinks about all these other kind of companies what are creating and providing these footprints. And of course, I need to say, Tom has his own company, and they have their own software. So, yeah, this is what you need to consider when you will be listening to the next clip. But I think I played or I included this clip in this video because I think he is right. And after I tried their software, I personally think it's a really good way how they do it. And especially when I saw all this background behind the software, what everything they do and what everything they know to create the software and put there all the knowledge, I think it's a really good way, maybe how in future I will be creating the footprints. I'm not saying I will buy their software or something, but I think it's quite good and interesting way to know how you, for example, can create footprints in the future. But I need to say, I know also the other people. I know Natasha from Snap EDA. We have met a couple of times, so I really think it's really great what they are doing in Snap EDA. But you will see in the clip there are a few things what I always pointed out when I was thinking about Snap EDA. I don't know how exactly it works there now, but who knows, maybe we will create another video where I will be speaking with Natasha about Snap EDA. If you don't know what Snap EDA is, they are also a company what are providing footprints and symbol and 3D models for libraries. You can Google for them. So here is the clip where Tom is speaking about all these kind of different companies what are providing footprints and 3D models and symbols and the things what can help you to build your libraries.
So you have all these different libraries, CAD vendors, component manufacturers, Ultra Librarian, Snap EDA, Maxis, Upverter. Everybody is using different things, but are they using all these things right here in this picture? Are they putting in an outline for the assembly drawing? Are they putting in an outline for the component body? Are they putting in the proper polarity markings? Are they putting in the proper paste masks for the thermal tabs? Are they putting in, all the information that's necessary by using some kind of rules and guidelines? Does Snap EDA have a guideline book? I'd like to see it. I'd like to know what rules are they building their library parts to? Are they using all the manufacturer's recommended patterns? And if they are they putting in an outline for the courtyard in their parts? Maybe not. Are they putting in an outline for the legend, an outline for the assembly, an outline for the components package? Maybe not. Are they putting in an outline for the polarity marking? I don't know. You know what I mean? Are they putting in an outline for the origin, for wherever the origin marking is? So I know where the center of gravity of the part is in the center, okay? Are they using rules like minimum pad to pad rules, minimum silk screen to pad rules, okay? So all these rules that we're talking about here are in library expert preferences. So I said we have 1,000 preferences, and the user can go into the preferences and then just change all the preferences that they want. The silk screen legend line width, the legend line gap, the assembly line width, what kind of polarity do you want? You could assign all these preferences, and then when you go to put in the package dimensions, it auto-generates a pattern per your preferences.
Yeah, this is what I found very interesting about the way how you actually create the footprints through your software, because I can specify basically my own standards what I use in my libraries, and you just press one button and it will generate exactly what I need. But if you go to internet, you never know on what layer they place silk screen, on what layer they place assembly drawing, or exactly as you said, what kind of rules were followed. Because I think Snap EDA they actually started as kind of community library, like
Yes.
different people were just pushing their footprints and their components into one single database, and now, is it like is the footprint right, or who created this footprint? Someone who is experienced engineer, or someone who just played on hobby project, or
right? And now let's say this. Let's say that you're an engineer or a designer, okay, and you're going out to all these different locations to get free library parts, right? You want to go to the component manufacturer and get a part. You want to go to the CAD vendor and get another part. You want to go to Snap EDA or somewhere Smaxis or whatever. Smaxis gives away free parts. You want to go to Smaxis and get a free part, right? And you want to go here and there and everywhere to get all these free. And when you put them all these free parts, and they all have different things on different layers and different sizes and different features, you're going to put these parts in the same PC board design, and it's going to look ugly. And we used to call printed circuit board design artwork. When we were hand taping, it was called artwork. It was like a piece of art. And that's why PC boards are art, okay? It's artwork. And you don't want to have a piece of art that's ugly. Who wants to create ugly art? You want to create pretty art. And when I have, the very first testimony that came across my desk when we first created this calculator was, Tom, I got your calculator, I built my whole library with it, I put all the parts in my design, and my design looks beautiful. And you know what? I just started learning how to design this year. I'm a brand new designer. I'm a rookie. I don't know how to design really, but your product makes my designs look beautiful. They make me look like a professional. So that's where we separate ourselves from the rest of the libraries out there in the world.
What to add? Very nice words. Okay, what we are doing, it's art. This way, I would like to thank you very much to Tom for his time, which he spent on the calls with me. And I would like to thank you very much for all the information what he provided. I think, as I said, I learned a lot, and I really hope you found this video useful, and also you maybe learn some new things. I would be very happy if you leave some comments under this video. If you have any questions for Tom, then leave your questions in the discussion under this video. And if you like this video, please don't forget press like button. Thank you very much for watching, and see you next time. Bye.